In this problem, the first thing that we have to do is to find how much work it takes to bring a charge, a test charge, or the charge, positive charge of Q into this space that is situated at a distance A away from this charge, right? This charge, which we'll call charge number 1, which is a negative Q charge, and then also another distance A that is located away from this charge right here, which is another negative Q, which we'll call charge number 2. And then finally, so basically just makes this square right here. And then finally, it is located a distance, of course, since A over square root of 2 times A distance away from this charge right here, because you're going to have an isosceles triangle because this one's the distance of A as well. So we're trying to figure out how much work it's going to take to bring some sort of charge in at that point right here. So that's our first step. And luckily, in this chapter, we were able to find a relationship between work and the potential, because potential is relatively easy to solve for that specific point. So we just have to find the potential at that point and then just multiply by the charge that we're bringing in there, because we're assuming that we're going to bring that charge in from infinity all the way here. So every step of the way we're doing work, and by doing work we're having to put in energy in order to get it to that point. Presumably energy could be negative energy or positive energy depending on the value of the charges for this. So for the first step, our Q that we're bringing in here is actually just Q, so it's the same magnitude of these charges here. And the next step, to find the potential right here, we just have to add up all the potentials that are being caused by each one of those charges that are essentially nailed down right there at their specific location. So I'll go ahead and explicitly write it out here. And I'll stay with the naming convention based off the numbers that I wrote right here. So of course we can express the potential in terms of so it's 1 over 4 pi epsilon naught times the charge that's causing the potential divided by the distance, right? So we all know that they all have 1 over 4 pi in common, so I'm just going to go ahead and pull that out of this bracket right here, and then all that's left is the ratio of the charge to the distance for each one of those. So for the charge for the distance for the first one is negative Q and a distance A away, so negative Q and a distance A away from that point. For the second one, of course, it is also a negative Q and a distance A away, negative Q and a distance A away over here. And lastly, for the third one, it's a distance square root of 2 times A and a magnitude of positive Q for that distance right there. And they all have Q in common, so I'll go ahead and pull that out. And you know what? They also have A in the denominator as well, so I'll go ahead and pull those out right now. So now we have, let's see here, Q squared over 4 pi epsilon naught times A. And then we can break all those down into a single relationship, which is square root of 2 over 2 minus 2. And that is how much work we'll need to bring in that test charge to that point. All right, so that next step, though, is how do we assemble that whole system? Right, so how do I, assuming you could do it any sequence, right? But the way I'm going to do it is just in terms of the numbers over here. So if I brought this negative Q charge and bring it all the way with assuming that these didn't exist yet. If I brought in this negative Q and brought it in from infinity, nailed it down here, and then brought in the second one and nailed it down, brought in the third one, nailed it down, brought in the fourth one, nailed it down, how much total work would that take? Right? So obviously, for the first one, it would take no work because there's no other charges nearby. For the second one, it would take the work to squish this one right next to this one, and then of course the work for the third one would be the work to pull it from infinity and squish it next to these ones, and finally the work that we just calculated right here. And the way we can express this mathematically, right, is of course we take the sum from the index from the very first one all the way to the n charges for the system that we have, and we just add up the work for each one of those, right? Or since we have a discrete system right now, we have the work from 1, work to bring in 2, the work to bring in 3, and finally the work to bring in 4. Which of course the work that we had to bring in 4 was the one that we just calculated right here. And it doesn't really matter what order that we go into, they should all add up to be the same. So we'll go ahead and start with curly bracket here. So like I hinted at, the work to bring in number 1 up here is 0, assuming that there's none of them exist yet. So the work to just move a charge in a vacuum to a certain location in a vacuum is 0. So we'll go ahead and put 0 right here. And then the work to bring in the charge number 2 right next to another charge that also has a negative Q charge. The work to bring in these, to smash these two together is going to be, of course, the same relationship that we have here, where it's the charge that you're bringing in times the potential that's from the system. So the potential caused by that one at that distance, which is of course square root of 2 times A. So negative Q is the charge that we're bringing up to it times the potential, which is 1 over 4 pi epsilon naught negative Q times square root of 2 times A. And again, because that is the distance right here, because we have a square. And then, so that's the work for number 2. The work for number 3 is the work that we to bring in this positive Q right here. And this probably should be negative, right? We shouldn't have to put in too much work to bring in a positive charge close to 2 negative charges. It should want to do that. So again, we'll keep this like how we said. So this is the Q times the potential. The potential is being caused by 2 different charges, so we're going to have to add up the potentials in this relationship here. So there's the Q, and then so the potential for 1 is actually they both have 1 over 4 pi epsilon naught in common, so both of the potentials. And so this distance from here to here is A, the distance here is A. They both have Q, negative Q right here, so it'll be negative Q times A to be caused by the charge number 1, and then the potential caused by charge number 2 is minus Q over A as well. And then finally, we have our work to bring in the 4th charge all the way here, assuming that these are now configured and nailed down, which we found that out already. It was this one right here, so we can just go ahead and plug this one in here. And so now, whenever we scroll down and we just gotta basically do some algebra and collapse these down together. They all have 1 over 4 pi epsilon naught in common. We'll go ahead and squish these down, so we now have a positive Q squared over square root of 2 times A minus a 2Q squared over A plus Q squared over A times the quantity of square root of 2 minus 2, because this is what we had up here. This is the answer that we had right here, square root of 2 minus 2. And then, there we go. Some more algebra happens. Let's see here, 1 over 4 pi epsilon naught. We'll pull out a Q squared over 2, which is common to everybody here. So now what we have is a positive 1 over square root of 2 minus 2 plus square root of 2 over 2 minus 2. And finally, that collapses down into, let's see here, 4 pi epsilon naught Q squared over A square root of 2 minus 4. So that is the work that it takes. That is the work that it takes, and I'll leave this here on the screen for a second, but that's the work it takes to bring all these charges in from infinity and to nail them down one by one. Well, technically, you don't even have to do it one by one, but to move them into infinity in order to get them into this this square configuration right here.